Okay, folks, so continuing where we left off, we're going to look at Chapter 4 homework, which involve I asked of the students problems 1, 4, 8, 9, and 10. Well, maybe a little bit more math involved, but that's what I asked of them. So, with that in mind, okay. So, let's get to the oh, nope, wrong thing. There we go. Sorry. Oh, ducky cam. Let's get this adjusted. So, problem 1. Problem 1 involves writing the general formula with the general formula of gasoline being C7H13. Calculate the air to gasoline mass ratio required for stoichiometric combustion. So the first thing we need to do is to write out a balanced combustion reaction for this. Well, it's going to be in presence of oxygen. Come on. O2. And the byproduct is always going to be CO2 and H2O. Now, while this is usually a big no-no, we can write this out as a fraction. That 7 carbons are needed to balance those 7, and for 13 hydrogens, since that's a factor of 2, that's what, to get 13 you'd have to have 6.5. So we'll say 13 halves. And so how many oxygens would that need? 4 times 7 is 14, plus another 6.5. That's going to put us somewhere like 20.5 oxygens. Well, to get 20.5, you're going to need something like, 10 of those guys would get you 20, and so 10.25. So 10.25, which would be the same as 40, would be essentially 41 over 4. 41 over 4. Yes, I know it's fractional. It's not pretty at all, but it will work. So, if for every 1 mole we need 41.25, we need 10.25 moles of oxygen, the next step is to convert these moles into mass. Convert these moles into mass to figure out how many grams of gasoline per grams of oxygen would we need for a stoichiometric mixture. So, the molar mass of oxygen is going to be 32 grams per mole. And the molar mass of this gasoline is going to be, so we're going to have 12 times 7 and 1 times 13. So 7 is going to be what? 70, 84 plus 13, something like 97 grams per mole. So what does that mean? I need 97 grams of gasoline per, so let's do that math, 10.25 times 32 is per 328 grams of oxygen. By that self, if we just asked for oxygen ratio, that would be perfect. We could do that as a mass percent. But it specifically, and this is what tricked me at first, it asked for a ratio of air. that air is not 100% oxygen. It's like 20.9% oxygen, or 20.1% oxygen. So, with that in mind, and then in fact, so 20.9% of this oxygen, how much extra oxygen would we need? So that is actually no good. Let's see. Since the 20.9% is not by mass, it is by, I think, volume, we have to factor that in. So we can have a direct correlation of moles to moles of air. So if we have 10.25 moles of oxygen that we need, 10.25 moles of oxygen, how many moles worth of air would we need? So dividing this by my 20.95%, how many moles of air would we need? So 10.25 divided by 0.2095 means we would need something like 48.93 moles of air. And the molar mass, the average molar mass of air, something like 28.96. So with that in mind, 48.93 times my 28.96 gives me something like 17 grams of air. Now let's see if I'd done it like that. So had I just tried to go from here to by mass, I would get a much larger number at 1565. So from that in mind, we have a mass of air per mass of fuel. So 117 per 97 can simplify to something like 14.6 per 1 grams of air per 1 gram of fuel. So the air needs to be 14, almost 14.5 times the mass of the fuel that we're entering in there. And the key here is, what makes this hard is the turning the moles of oxygen into moles of air there and not there. Had I done it at the later step, I would have gotten something like 16.1 to 1 ratio. So a lot higher, not what we wanted. So that one's a little bit trickier, but hopefully my guidance can make this somewhat reasonable. So. Now, for the peroxyacetic, nitric, anhydride can be thought as related to hydrogen peroxide. Draw the structure and indicate why you suppose this is a powerful oxidizing agent. So the idea is that it's a structure of hydrogen peroxide and nitrate. So peroxyacetic. So acetic acid looks like something like this: CH3COOH. Now peroxyacetic nitric acid has a A acetic acid has a structure similar to this. So, proxy acetic, and this guy is stabilized to some extent by conjugation, by resonance. So, with that in mind, drawing these together, the proxy acetic nitrate, so it's going to look something like this. CH3 is part of the acetic, CO, then O, O, N, O, O. So it's combining. Nitric acid is particularly reactive because it has the dual charges of the plus and the minus. Peroxides are particularly reactive because they have the unstable oxidation state of -1 on each oxygen. So, and the nitric acid has the formal charge of essentially oxidation state of 5+ on that atom. So this combines kind of the reactivity of both. The peroxide, which is naturally charged with the oxidation state of 1-, and the nitrate, which is prone to oxidation as well. Both of these are strong oxidizers. Nitric acid is a strong oxidizer by itself. Peroxides are strong oxidizers by themselves. Combined together, you're getting an increase on the oxidation value on both of those. So that one is not meant to be overly challenging other than to really kind of think of the structure behind that. Oh, not 5, but 8. Now, problem 8. Problem 8. Canadian companies developing a process for converting agricultural waste, straw, wood chips, etc., to ethanol. This is an advance on the current technology that uses high-value feedstock, say corn, cane sugar, etc. For the process, the company claims there is the potential to produce 300 liters of ethanol and 300 liters of C2H6O from 1 ton. From 1 ton of waste. 1 ton of waste. Using the information on the fermentation of the biomass to calculate the efficiency in terms of mass of this process. The density of ethanol, the density is 0.79 grams per mil. So, we're considering the following reaction, that of a simple biomass, CH2O, that's the generic biomass thing. 3 of those are needed to convert to ethanol, the C2H6O, and a CO2. That conversion of that to that. So the first question is, considering this process, how much ethanol could be produced if I took 1,000 grams of this biomass and assumed 100% conversion into this? 1,000 kilograms. 1,000. So using that, so 1,000 kilograms. The molar mass of the biomass of each of those units is 12 plus 2 plus 16, so 30, and then we triple it, so it's going to be something like 90 kilograms per 1 kilomole. And the molar mass of this guy mole mass of this guy would be 12 times 2 plus 6 plus 16. So the mole mass of this guy is going to be something like 46 grams per mole. Or 6 grams per mole. So, meaning if we produce 1 mole of this for every 1 mole of that, so 1 mole of reactant is going to give me 1 mole of product. That means we would be able to get 1 kilomole, would be able to get 46 kilograms. So 1,000 divided by 90 times 46 means we would only be able to get 511.1 kilograms of ethanol. So, with that in mind, we need to convert that into volume. Now, why did I particularly choose 1,000 kilograms? Because 1,000 kilograms is a metric ton. So 1,000 kilograms, so 1 ton. So how much volume would this be? So if the density is 0.79 grams per milliliter, that means there'd be 0.79 kilograms per 1 liter. So dividing by 511.11 by my 0.79, we would get, this would produce, hypothetically, 646 we'll say 0.97. We're going to round to, let's say 647 liters. So that's assuming 100%. So if I'm supposed to get 647 and I produce 300, the efficiency would be something like 300 divided by 647 gives me an efficiency of something like 46.4%. 46.4%. Not great, but the fact of the matter is we are not wasting any of our fuel. We are not wasting something that can use to feed an animal or feed a person. So that is why that is better. Well, even if it may or may not be as efficient. Now, with that in mind, number nine. For internal combustion engines, ethanol is used as a gasoline additive to increase the oxygenating ability of fuel, or it can be used as fuel alone. So, vehicles in Brazil have engines that are modified so they can burn ethanol as fuel. Compare the mass fuel to air ratio on a mass basis. The mass fuel to air ratio required for complete combustion of heptane versus ethanol. So the product of this, regardless of which, is CO2 and water. So we need to write the chemical reactions. It's basically we have to recreate problem number 1 again, except instead of we're going to work with not just heptane, we're going to use heptane instead of the ethanol version we used before, and we're going to use our methanol. So heptane first is C7H16, which will make the balancing a lot easier. So O2, CO2, and water. So 7 carbons, 8 hydrogen, 8 waters. So 8 plus 14 means we have 22, so that means we're going to need 11 oxygens. Well, that's pretty straightforward. For ethanol, C2H6O, we will have oxygen, but we have an oxygen source there. CO2 and water. Well, we're going to need 3 there, 2 there. We have 2, that's 4 plus 3, so a total of 7 oxygens. But because one of them's coming from there, we only need 3 oxygens. So, of my 11 moles of oxygen, we're going to divide that by my 0.2095, and then we're going to multiply that by my 28.96, which is my average molar mass of air. The same as we did for problem 1. So 11 divided by 0.2095 and times my molar mass, 8.96, means we're going to need something like 1520.6 grams of air. And the other guy, 3 divided by my 0.2095 times my 28.96. It's going to be something like 414.7 grams of air. Well, the molar mass of heptane, 7 times 12 plus 16 is something like 100 grams per mole. Ethanol, we just talked about that previous problem, was 46 grams per mole. So, the fuel to air ratio, divide that by 100. So, for heptane, it takes something like 15.2 grams of air per 1 gram of heptane. For the ethanol, we're going to divide the 414.7 divided by 46. It takes something like 9.0 grams of air per 1 gram of ethanol. So ethanol needs a lot less air to burn in a stoichiometric ratio. So you can see that is a lot less, almost half as much. Finally, the last problem, problem 10. Methanol can be used as a fuel in specifically designed engines. Calculate the energy density on the combustion per mass of fuel with that of octane. Comment on the relative merits of the two fuels in terms of environmental and practical issues. So, with this in mind, this one might be a little bit more in depth. So, first thing is we gotta write the balanced chemical reactions for these, and then we have to do a little bit something we haven't done yet. So, ethane. Methanol, it'd be CH4O. And we have O2. And we have, going to go to CO2. And H2O. So with this in mind, you're going to have to, in order to get this to balance out right now it would be 1 and 2, but that would produce 3 oxygens and what? Let's see. Well, that would produce 4 oxygens, and in order for this to balance out, we would have to double things. So I'm going to put 2 here. 2 there, and that means there's going to be a 4 there. So we have 4 plus 8 oxygens. We get 2 there, so we need 3 here. This is a balanced chemical equation. Make our life a little bit easier. For octane, it's C8H18. And you're going to have O2. You're going to have a similar problem, CO2, H2O. The problem is you're going to have 9, and you're going to have 8 and 9. So this, once again, you're going to have to double this. 18, 16, 25. This is just so that we have the right enthalpies. Okay, that in mind. Now, to do enthalpy reactions, we need one key thing. We need to look up on our table the relative enthalpies of combustions for certain molecules. So we need the enthalpy values of methanol being negative 238.66. The enthalpy of pure oxygen is always 0. The enthalpy of octane, 249.95. The enthalpy of CO2 is 393.51. And the enthalpy of water is something like negative 285.83. So, to calculate enthalpy, it's always going to be products minus reactants. So, for methanol, for the given chemical equation, you would have negative 285.83 times 4 and negative 393.51 times 2 minus 238.66 times 2. So negative 285.83 times 4, and then negative 393.51 times 2. 238. You get something like, the enthalpy of that reaction being something like negative 1453.02 kilojoules. However, this reaction requires 2 moles of methanol. So if we divide that by 2, you would get the moles of methanol per the reaction per mole of methanol. 26.5 kilojoules per 1 mole of methanol. Doing the same thing with octane. So we get negative 393.51 times 16 and plus a negative 285.83 times 18 minus a negative 249.95 times 2. So doing that quick calculation, this one's going to be a lot bigger of a number, but 5.83 times 18, 49.95 times 2. So you get something like, negative 10,941.2 kilojoules, and then we divide that by 2. Sound like still a big number, negative 5,470.6 kilojoules per mole of octane. But all that's per mole. That's per mole. That's not per gram. That is not per That doesn't tell us a lot because 1 mole is essentially 1 molecule. So, methanol, 12 plus 16 plus 4 weighs something like 32 grams per mole. Octane, with its 8 times 12 and 18 times 1, is something like 114. So with that in mind, calculating this as kilojoules per gram, the methanol would be negative 726.5 divided by 32 grams per mole. So 726.5 divided by 32, and you've got something like 22.7 kilojoules per gram of methanol. Now the other guy, 470.6, we divide that by 114. 470.6, we divide that by 114, and we get something like, negative 47, we'll say around that 48.0 kilojoules per gram. Now, with that in mind, octane is still way more energy dense. We have almost twice the amount of energy in octane than we do in methanol. However, as we just saw in the last problem, because it has oxygen, it's going to burn far more fuel efficiently. Far more fuel efficiently. Like if we looked at it under the same basis, so 3 divided by, let's see, 14.7 divided by 46, but 64, you would need only like a 6.5 to 1 ratio of air to fuel for this to completely combust. And even then, it's going to produce, like on a per carbon basis, if we looked at it on a per carbon basis in terms of fuel, this produces 22 kilojoules per carbon, while this produces actually only something close to 6. This is actually 6 kilojoules per carbon versus 22. So, in terms of a carbon CO2 production scale, this is going to pollute far less for the same amount of fuel. It's going to need far less air for this to burn completely, so probably less chance of producing nitrogen oxides. And but the main thing octane has going for it is that it's very energy dense, so you wouldn't have to fill up the car as often. You could travel further on the same weight of fuel. So there's some push and pull. And obviously, if you have to go through a bunch of extra steps to produce methanol, well, then that's another problem in itself. But with that in mind, that's the kind of thought processes people need to start considering as we do some of this stuff. Like, is this truly what's best? But okay, with that in mind, that's the end of this homework assignment. Thank you for your time.